In this short video, we're going to see how to solve for the input demand curves when we're in the long run. Let's imagine that Loaf and Behold is a local bakery that produces bread. They operate with the production function Q equals 9LK plus K. So we have to be a little careful with our font here. Q is a little lower, 9 is a little higher, and my apologies for the fact that this font is not good at distinguishing between 9s and Qs. So in this question, L is hours of labor hired and K is hours of capital hired. We're also told that the price of labor is W per hour and the price of capital is R per hour. Our goal is to determine Loaf and Behold's long-run demand for capital. What do we need to know to answer this question? We just need to know the production function. How should we go about solving this question? Just like a cost minimization problem, except we may not have specific values for wage, rent, or an output goal. Here is like the worst case scenario because I have not provided a wage, I have not provided a rent, and I didn't tell you an output goal. At a minimum, if you're solving for the demand for capital or labor, you should see at least one of these values missing. Let's see how we go about solving for this demand curve. So here's what we know. We know that the production function is 9L times K plus K. We are trying to find the long-run demand for capital. We're going to solve this using standard methodology, which means we need to find the marginal products, the tangency condition, and we also need to establish the isoquant condition. So the marginal product of labor is the partial derivative of the production function with respect to L. That's going to be equal to 9K. And the marginal product of capital is the partial with respect to K, which will be 9L plus 1. From here, we can compute our tangency condition. So the tangency condition says that the marginal product of labor, which is 9K, divided by the marginal product of capital, which is 9L plus 1, has to be equal to the wage over the rent. This question does not specify a wage or a rent, so we're just going to use the placeholder values. We also need to write down our isoquant condition. Don't be confused. This question does not specify an output goal, so the output goal is just some Q. I'm going to use a lowercase q because that's a sort of convention, but you could use a capital Q if you wanted to. So I just take my production function, 9L times K plus K, and I set it equal to Q. So we'll call our tangency condition equation 1 and our isoquant condition equation 2. Now that we've established our tangency condition and our isoquant condition, I think it's really helpful to make a little bit of a plan for how we're going to proceed. It starts by recognizing what we're trying to do. We're trying to find the long-run demand for capital. Because we're looking for capital, what we want to do is we want to take our tangency condition and solve it for L. That L will depend on capital, and we'll be able to plug that L equation into the isoquant condition to isolate K. So the first thing that we're going to do is we're going to solve one for L, and this solving is annoying, I'm going to admit it. So we'll start by multiplying top and bottom of the tangency condition by 9L plus 1. That gives us the following. 9K is equal to W over R times 9L plus 1. Now I keep in mind I'm looking for L, so I have to get rid of this W over R. So I'm going to multiply both sides of the equation by R over W, and I'll end up with 9K times R over W is equal to 9L plus 1. Now I'm going to subtract 1 from both sides, so I have 9K times R over W minus 1 is equal to 9L. And to finally isolate L, we have to divide the whole thing by 9. So I end up with L is equal to 9K R over W divided by 9. So the 9 disappears, so I have K times R over W, and then minus 1 over 9. So that was not fun. We're going to call that equation 3. The next step is to take equation 3 and substitute it into 3, that isoquant condition. So what I mean by that is I'm going to take this big ugly equation 3, and in place of L, I'm going to put that. So I have 9 K times R over W minus 1/9. That's L. Don't forget about the K, times K plus K is equal to Q. It's ugly, but we're going to make it work. Now we can do some simplification. So I'm going to start distributing this 9 term in. So I have 9K times R over W minus 9 times 1/9, which is 1, all times K plus K equals Q. Keep in mind that we're trying to find K. So now I'm going to distribute this K into both of these terms. So I have 9K squared times R over W minus K plus K is equal to Q. I breathe a brief sigh of relief because these two K's cancel. And I can rewrite this as 9K squared times R over W is equal to Q. Now I want to solve for K. So I'm going to first isolate K squared. I have K squared is equal to Q divided by 9 times, let's see, well, to get this R over W to the other side, I multiply it by W over R. So times W over R. I'm almost done, which is good because I'm out of space on the slide. So to finally find K, what do I need to do? I need to take the square root of both sides or raise both sides of this equation to the 1/2 power. So I have K is equal to Q over 9. Actually, let's write it this way. Q times W over 9 times R to the 0.5 power, which you could simplify. Only one little bit simplifies. 9 to the 0.5 power is 3. So we could write this as 1/3 QW over R all to the 0.5 power. QW over R all to the 0.5 power. I hope you recognize that this was quite a challenging question. Ask yourself why it was so challenging. It's actually for a couple of reasons, because I did not tell you W, R, or Q, which is why our final solution has all 3 unspecified exogenous variables in it. It's also difficult because of the structure of the production function. It's not a Cobb-Douglas, it's like a Cobb-Douglas plus because it has this extra plus K term in it, and that made this very algebraically difficult.